Welcome back. In the last set of videos, we covered the basis of both the function model as well as the object model for our subsystem. In this video, we will learn about the dynamic model. The dynamic model describes the internal behavior of our system. Specifically, it outlines how objects in a system collaborate with each other to accomplish various use cases. Once we start to define our services and the interfaces within our subsystem, we are ready to build the dynamic model. A service object provides a set of business logic related functions. For example, the ticketing service class may allow you to buy tickets, sell tickets, redeem tickets, and so on. Generally, these functions are publicly accessible and are called as the interface for the service. If you remember, we used the use case diagram to represent the functional model, and we used the class diagram to represent the object model. In case of dynamic model, we can use both the sequence diagram as well as the state diagram to represent the dynamic model for our subsystem. Let's learn about the sequence diagram and the state diagram and see how they convey information about a system. To start off, a sequence diagram is a type of interaction diagram, and it describes not only how and in what order a group of objects or services interact with each other. A sequence diagram is generally used to represent collaboration and flow of information across the participating objects for a given use case. On the other hand, a state diagram shows an illustration of states an object can attain as well as the transition between those states. A state diagram is also known as a state machine or a state chart diagram. As you see, both of these type of diagrams convey the internal behavior of a system. The sequence diagram conveys the internal behavior of a subsystem through interaction of services, while the state diagram shows the inner state of a given object through its transition from one state to another. Let's go through a high-level example of each of these diagrams to understand more. To recap, a sequence diagram shows an ordered sequence of events or information flow between a group of objects or services. The order of events or the information flow can be traced by the arrows. A solid arrow represents a request, while a dotted arrow represents a response. We will build a sequence diagram for the buy tickets use case for our concert app. As a part of the use case, the fan searches for an event they like to attend and purchases a ticket for that event. To begin with, we list all the actors and the components that interact in this given use case. We have the fan that wants to purchase a ticket for an event, the event service. This service is responsible for returning a list of matching events. The ticketing service. This service is responsible for creating the ticket. The payment service. This service is responsible for charging the user's payment method, for example the credit card, in order to capture the ticket fee. All these services, the event service, the ticketing service, are essentially objects, that is, instances of the respective class, and has properties and functions. In a sequence diagram, we are interested in functions that are exposed by these objects, and we want to show how those functions are invoked across a set of objects while fulfilling a given use case. Here's how the sequence events plays out for our given use case, that is buy tickets. The fan searches for the concert events that they are interested in. Behind the scenes, we invoke the search events function against the event service. The event service is responsible for returning the list of events matching the search criteria that was provided by the user. A list of matching events is then displayed back to the user. The user chooses an event that they like to attend and initiates the ticket purchase flow. Again, behind the scenes, we invoke the buy ticket function of the ticketing service and provide the following details. We provide the information about the user who wants to purchase the ticket, the event for which the ticket has to be purchased, the payment method that was provided by the user in order to pay for the ticket. The ticketing service does some basic validation of the input and calls the payment service in order to secure the payment. The ticketing service waits for the response of the payment service before it can issue the ticket. The payment service takes in the payment details and sends in a request to the payment processor in order to charge the ticket fee. The payment processor charges the ticket fee and returns the response back to the payment service, which further sends the response back to the ticketing service. The ticketing service inspects the payment results, and if the payment was successfully captured, it creates a ticket into the database and finally returns the details of the ticket. Then we show the ticket confirmation back to the user. Generally, a sync request and response model is used where an object sends in the request to another object and waits for its response. However, depending on the type of service, asynchronous model of communication can also be used. Now let's look at the state diagram. To recall, the state diagram shows the various states that an object can attain, as well as the transition between those states. For our app, let's look at the state diagram for our entity, the ticket. And we will understand how its state changes due to the various events and activities. To begin with, in a state diagram, the begin state is marked with a black filled circle, while the end state is marked with a black filled circle having a white outline. This helps us to distinguish between the begin and the end states. We call our begin state as non-existent. This represents that the ticket has not been created yet. Now then, when the user buys the ticket, we create the ticket and its state is set to reserved. When the user attends the event, the state of the ticket changes to redeemed. Once the ticket has been redeemed, its state cannot be changed anymore, as is shown with the line leading to the end state. Alternatively, if the user does not want to attend the event, they can cancel the ticket, and the ticket state changes to cancel. Once the ticket has been cancelled, its state cannot be changed anymore. Again, this is shown by the line leading to the end state. Thus, redeemed and cancel are the final state, while non-existent is the initial state. The state diagrams helps us to understand how the state of the ticket changes due to the various events in interaction and how we can use those state changes to perform actions in a decoupled way. For example, when the ticket state changes to reserved, another system can observe that event and it can use it to send out purchase notification to user. This concludes our intro to dynamic models. We walked through an example of both the sequence and the state diagrams to show the inner details of a system. Hope you got a high-level understanding of the various types of models that we can create to represent any subsystem. We will continue with another important topic, the system design activities, in a subsequent video. Till then, thank you, and we'll see you in the next video.